Good morning and welcome to Physical Science in the AM. Thank you, Mikey. Okay, we're going to look at this, energy changes in chemical reactions. It's basically a continuation of the other, but we're focusing more on chemistry than the physics aspect. The other day we talked about the idea of temperature and heat. They're kind of different things. They're related. We use them in everyday language as almost the same thing. But let's just talk about the heat energy involved in reactions. Why do chemical reactions occur is our first question. Well, a couple things. Think about it. One, the products of the reaction have less energy than the reactants. We'll see this on a graph and it might make more sense. But essentially, if a reaction occurs quite often, it's not a must. It's one or the other, or sometimes both of these two. So, less energetic products drive a reaction. Then and/or I have there too. The products are more at random or less ordered than the reactants. We have a word for this concept, entropy, and it's kind of a mathematical concept. But we won't get into how to calculate it and stuff. That's physics. Well, it's related. But anyway, that's what we have. Now, within this is when we study energy reactions and stuff like this, chemical reactions, we call it thermodynamics. Study of energy and energy movement. So it's not just reactions, but we're going to focus on thermodynamics with the other chemical reactions. Now, to review a little bit, heat is the thermal energy that's transferred from one to another, one body to another. It's measured in joules, that's energy. Heat is always transferred from high temperature to a low temperature object. You don't talk about joules much outside of the science classroom, but quite often when you look at the calories on food, I'm going to just grab a slide and see. Generally lists the calories. Calories measure the same thing, it's just a different unit. I'm just taking a look. No, this one does not measure the joules. Sometimes they have in brackets the J joules. Anyhow, the calories you get from food could be measured in joules. It's energy, just like the energy transferred from one object to another measured in joules. Same kind of concept, but it seems quite different. But same kind of concept, energy. Temperature is a measure of the average kinetic energy of the particles. We talked about this a little bit, and that's a bit of a review. Celsius is our most common energy, or most common temperature unit. But we can convert to Kelvin by adding or subtracting. 273, you can go back and forth between Celsius and Kelvin. We practice that. Fahrenheit is also used. That's more of a US thing. But you come across it the odd time, but not in the science classroom. I'm going to pause and update this. To continue, laws of heat movement. We're not going to go through all of the laws of physics of thermodynamics. A couple of things. First law of thermodynamics is energy is conserved. It's never lost or gained, it only changes form throughout the universe. This applies not just to chemical reactions, it applies to traffic collisions, it applies to sliding down a slide and stuff like that. I'm not going to get into it too much. You'll see a lot more of it if you take physics 30. And that's not just thermodynamics. But anyways, second law of thermodynamics, heat always moves spontaneously from warm to cold. Now, we saw this, and we're going to practice this once again. That's why I'm kind of whizzing through without going over the other thing, because we're going to take a look at Q equals MC delta T, but first I'll update once again. And Bushra, you know to come up here. Okay, as I was saying, anyways, Q equals MC delta T. We've seen this before. We'll continue using it. Hopefully we get some experiments and measure it. But let's just practice this. 2,000 liters of water is heated from 11 to 21 degrees Celsius. Find the quantity of heat added to the water. Now, underneath I have something added though, so we can figure something out. And I will. The density of water is about 1 gram per mil. So we're going to use that. And the heat capacity, the C value of water, I'm going to use is 4.19 joules per gram degree Celsius. Now, we were given a volume of water, 2,000 liters. That's a lot of water, right? Oh, so maybe this is a hot tub or something. And the heat energy is provided by the electric heating system in the hot tub. 2,000 liters. We need a mass though. And if 1 gram is 1 mil, kind of jump some steps on here where I say, well, 2,000 liters is 2,000 kilograms. I'll explain the reason. 1 gram, 1 mil, and I won't put that on. Well, 2,000 liters, here's what I did in my head, is how many milliliters? Multiplied by 1,000, that's 2 million. And 2 million milliliters is 1 gram per mil, that's pretty easy. That's 2 million grams. So it depends on that date. That's another way. Okay. This may be more direct. Now we have the mass of the water we're using. It's important it's liquid water. The other day I gave you a sheet with the actual, a bunch of different C values. We'll pause and listen to this. That name sounds made up. It is. They're just interrupting. Sorry for the interruption. No, okay. Now the C value is given, and that's for liquid water. MC, we need a change in temperature. This one I can do in my head. Final minus initial, so 21 minus 11, so that's 10 degrees Celsius or Kelvin, you can say. It's always final minus initial, by the way, because if water was losing heat, you were cooling it off, you would have a negative change in temperature. So I'm going to just underline this. We're doing this in our head. Change temperature equal to 10 degrees Celsius. And I know that this is two significant digits because I just did the subtraction. This is fairly easy now. The energy, Q equals MC delta T. Which is 2 million grams. C, 4.19. Temperature is 10. That's pretty easy to do with math. On the calculator. I don't get to the end. 2 times 4.19 times 10. 838 0 0 0 0 0. I'm going to write that down. Around. Let me see there. I'm going to space the number. count of the zeros and choice for her. 800, 0, 1, 2. Okay. 83,800,000. We only have two significant digits. I'm going to call that 84. Still pretty big. We could use kilojoules, and that's common. For kilo, 1,000. It doesn't matter if it's kilometer, kilogram, or whatever. It's 1,000 of the base. I could just do that this year. There we are. Okay. However, this is just fine. I didn't state what units you need to do. But we're going to be using kilojoules a lot. Because it makes the numbers smaller, easier to work with. Any questions at this point? This is kind of a review and tying it into chemistry. Review of the other day. Okay. You're wondering why I have a star and stuff on the side, by the way. That has worked out. So, same thing. That's what that's all about. I will pause and change the video thing, or the screen. So relating energy to chemistry. Energy changes. Energy? Energy changes during physical, chemical, and nuclear reactions. We use the term enthalpy in these cases when it's reaction. And triangle H, delta H, Greek letter delta, that means change. And it's a symbol for enthalpy change, heat energy change. Now, taking a look here. There's a physical change there. It's an ionic compound, ammonium nitrate. Basically, if you drop it in water, you can tell because it's aqueous. That's not really a huge chemical change. It's like dropping table salt into water and swirling it up. Ions separate in the water, but it's not a chemical change. You could just evaporate the water. You start with you'd have the same starting material. But there's a delta H at the end, positive 27 kilojoules. And that's the energy involved in this. Let's call it physical change. Because atoms, molecules, etc., and physical change do not change. Okay. Nuclear fusion. Here's an example. I can roll it just because. Yeah, there's what you know about nuclear energy. There's huge amounts of energy. Okay? So we're going to focus though on chemical change. I just showed you two examples. Oh, tired already. It's crazy. So I mentioned we're going to look at graphs, and here we are. Representing enthalpy changes, and that's energy changes in a chemical reaction. Okay? We can use a graph. Now I'm going to just take a look at this. Where you get used to the word enthalpy, energy, change. This is a scale where I didn't put 0, 1, 2, 3, 4, you know. The same increases as you go up on this graph. And this is like the reaction progress time as the reaction proceeds. If you start okay. You notice we have hydrogen plus oxygen in this reaction occurred before making water. We start at high energy. Remember, one of two things have to happen. This would be one where you reduce the amount of energy. It drops 486.3 kilojoules. That's what drives this reaction. end up molecules of water. That means the hydrogen plus oxygen means it gives off, it releases a lot of energy, 486.3 kilojoules per 2 moles of hydrogen involved, per 1 mole of oxygen involved. If you look at the balance. Now, so there's the graph, and it clearly shows just visually that you're dropping the energy. But there's two other ways to do it. You could show it within the reaction or written separately, and here I go. So this particular reaction, this is what we're going to learn from a graph, how to interchange between any given one, you should come up with the other two. You notice what it starts with. These are our reactants. Okay, we're going to start with that. 2H2 plus O2. Oh, I mean this. I'm going to put in the little g's here. It wasn't in the graph. That means they're gases. What you make is two waters. The water vapor gas. And it gives off, when it says loses energy, minus 486, like, that means it's throwing it out. It's also a product. So we're going to put it here, products. That gives me the exact same information that's given in the graph. If that reaction required energy, I would put 486.3 kilojoules on the left-hand side. Oh. Decreasing or throwing the energy out. Correct. You don't use the negative sign. All the negative sign means is leaving the energy system. We have a word for that. Exothermic reaction. We'll talk about that word later on. That's correct. Now, you can also write it separately. Now, I kind of showed you that physical reaction, but I'll go through it again. So this almost looks the same. Listen to different color. We still start. Same reactant and products chemical-wise. This time we don't show the energy inside the reaction. We can write it separately. I put it at the tail end, but it's not inside the reaction. Sort of like that. I'll put a comma here. You don't need it. Just to show it's not inside the reaction. Delta H. So enthalpy change. I'll make my H look like this. Is equal to minus 486. Negative 486. There's three ways of writing. Graph, energy, part of the reaction, or delta H notation itself. Whether it goes underneath, delta H is written before, it doesn't matter. That's the energy involved in that. Now, in practice, going back and forth, representation. Okay. watching it. We're on strike. Work. Okay. Oh. We're going to take a look at this. This is your next page, correct? So I'm waiting for you to flip to it. Awesome. You're not doing it. Represent this information in three ways with whole numbers of the balance. So how does this balance when I have a fraction? Let's see this. You're going to get used to this sometimes when you have fractions. The very first thing we need to do is 1, 704 kilojoules. This is the 1, and this is 3 halves. To get rid of a fraction, what do we multiply everything by? If there's a fraction on 2, we multiply by 2. Left and right side, including energy. So that's going to be the first way we represent this. We'll just do this together. So here's one way. Multiply everything by 2, and we'll get this. This will be energy within the reaction. So, times 2. So 2 AL equals 3. I'm really cracking straight. Are you ready? 2 times 700 is 1,400. So, with the 4 times 2 is 8. 1,400. 1,400. Notice that the energy on this one is on the opposite side. Part of the reaction. This reaction requires energy. I'm going to give off energy. If this happened in a test tube or something like that, the cool to actually draw the energy. So then the tool amounts. Design this to get rid of the fraction, so 3 halves times 2 is 3. Now, a review. What kind of reaction is this? Don't even worry about the energy part, but if it's just AlCl3, one thing breaks up into 2. We took 5 different types of reaction types. It's not combustion, oxygen. What is this when you have one thing breaking up into a couple of things? Decomposition. You need to know this. Good. Now, you know what? With core, I already you asked something, and I said it's an exothermic reaction. This one's called endothermic. I'm going to bring it up now. We'll formally pick it up later, but I'm going to put this down. This, and you are too. This is an endothermic reaction. This wasn't directly asking. Might as well talk about analysis. That means energy is required. It's not given off. Okay. What word association? Endothermic. Energy ends up inside the reactor. The opposite dimension, though. Exothermic energy exits the system, leaves the system. Okay. Just get used to these words. Now, a second way to represent energy. Do we want to do the graph or the delta H notation? Let's do the delta H notation. So basically what that means is you're not writing energy in the reaction. You're just writing down those items without the delta H. or without the energy involved. Then you write it out. So it's just simple. 2AlCl3 decomposes to. Then after it, I'm going to write down delta H equals, and because it's ending up in this number, I'm going to use a plus sign, 1400. I didn't need the plus sign, but I'm emphasizing that it's positive change. You write 1400. Okay, so that's the same information given in one. Write it as delta H separate. Let's do the graph now. So with the graph, I'm thinking it increases in energy. That means on our graph, we're not going to put a scale on it, but it goes up. Read the graph from left to right. So go like this. I'm going to put the word envelope here, or just I'll just put an E. You can think of it as energy, but energy is going up. And low on the graph, I'll draw an axis first of all. This is the reaction coordinates, sort of like time. The reaction goes. You start low in energy, and it's a 2AlCl3. Let's say it has this low energy. I don't have a scale, so it's not exactly. It goes up in energy. I'm going to write down how much energy. Oh, I'm going to down. These get and it goes up. Produces aluminum and chlorine. Okay, there we go. They're all three. Put back together page before I go to talk about the words everyone. Okay, we'll put that. Will too. Previous page. Endoaction. You guys use the word endoaction during the Big Ten? Could have, and that's kind of what I was. But anyway, it doesn't matter. Underneath this third written separately example here, let's write down this. This is exothermic reaction. Why is it exothermic? Because energy negative, it leaves the system, it exits the system. I'm saying exit though because of the word association with X. Oh. Energy exits the reaction. Okay? And that'll always be on the right-hand side if you have it built into the reaction. And it'll be a delta H that's negative. Grab the low